COVID-19 is a pandemic which has 245 million cases and caused about 5 million deaths around the world. Rather than a health issue, many countries have experienced economic recession because of it. In our project, we aim to achieve higher predictive performance on COVID-19 new cases and unemployment rates by including and modifying existing models. This is the structure of our presentation, and we will introduce to you the methodology and implementation of our models one by one. For COVID-19 new cases focus, SEIR model and the time series model have shown to be two mainstream focusing frameworks. Among various modified SEIR models, the Delphi model takes the government response into account. The policy simulator model further considers vaccination status. Here leaves us a space in combining existing models and construct a more realistic model. While follow the work by Hafner, VAR has also shown a good effect on fitting the new cases curve. So which model framework works better? The unique point in our project is that we apply two different model frameworks. Besides combining their results, we further compare their advantages and limitations. In the first part, I will introduce how we apply an adaptive SEIR model in focusing the COVID-19 new cases. In SEIR model, individuals are classified into the following four infection categories. It uses ODE function to characterize individuals' one-direction movements. This is how a basic SEIR model works. When a susceptible individual contacts an infectious individual, the susceptible individual becomes exposed with a probability R beta. Then it takes several days to turn an exposed individual into infectious, who can actually spread the disease. We measure it by epsilon here. After that, the infectious people are removed from the crowd at the speed of gamma. In our model, we modify the basic SEIR model from 3 points. First, we further divide people in 3 vaccination status. They transfer under the control of the parameter V and have different possibility in being infected. Second, we design a framework to take government response into account in a model by parameter P. Third, we consider the delay and miss in cases reports. This page demonstrates how we construct our ODE set. Then the question comes to how to estimate the parameters inside. For some parameters, we set a fixed point referred to the existing research. For vaccination transfer rates, we apply logistic model to do the focus and fix the missing points. For government response measurement, we refer to the predictive values given by Delphi model. It retrieves the normalized government response measurement by constructing a regression tree. For the remaining parameters, we use historical data to calibrate its value. We select the data showing the smallest modified weighted RMSE in historical performance. Otherwise, as we observe alpha trend, we calibrate alpha in the following 3 modes. In UK and Singapore cases, the constant one works well. In US cases, the linear one stands out. Thus, we calibrate the alpha value in different forms for different countries. How to set the initial point and data is another key problem. Here illustrate our initial point calculation methods and where our data comes from. This is a brief introduction to our SEIR model framework. The model results will be introduced in the following section.
For this part, let me introduce the VAR model. And for the data, we use time series of the difference of daily new cases of the 3 countries. And we can plot them and the CCM plot. From the 2 figures above, we can see that cases in Singapore have few relationship with the cases in the United States and the United Kingdom. And we use VIC criteria, set the lag order equals to 7, and then simplify the model by omitting the coefficients whose significance is below 5%. And the formula turns out that our guess is right, that the cases in Singapore have fewer relationship with the cases in UK and the US. And here is the CCM plot of the residues and the box test results of the residues. From the statistics of the residues, we can see that our model fit the sample very well. And as for the prediction part, it will be presented by my group mate later.
As the prediction accuracy, since the situation performance on these 3 countries are quite similar, we will then focus on the prediction in Singapore cases. And the error also shows that the average of these 2 models has the best prediction accuracy. And we further investigated its performance from June to October. and its result was similar to the previous slide. So we choose the average of ACIR and VAR to predict the COVID-19 new cases. And we also find something interesting in our models. With the increase of data frequencies, the prediction accuracies can increase, which can be shown from the error plot table in the left right. And that the error was decreasing from months to 14 days and 7 days. We think that with more data, we can capture more spikes, which result in more accuracy of prediction. Besides, our model also have some practical significance. The two-dose trend reduction in the ACIR parameter was similar to the trend of the vaccination rate in Singapore, which shows that the vaccine is becoming invalid. And the remove parameter in the ACIR model is similar to the trend of new deaths. In conclusion, there are something that can further be done. The first one is to improve the speed of collaboration. And the second one is to add more factors like the number of ICU patients to increase the prediction accuracy. And that's the end of our forecast on COVID-19 new cases. Next part will be our forecast on unemployment rate.
Now let's talk about unemployment rate forecasting. For existing works in literature, ARIMA models and other time series models such as GM and GVM are widely used. Besides, using hybrid methods to achieve more accurate results is the main way. However, limitation is that during uncertain periods or sudden shock, the accuracy of models declines. The method we use is a hybrid methodology. The idea is that we want to capture the linear and nonlinear patterns of an unemployment rate series separately and add them together to get the prediction. For linear parts, we use ARIMA and ARIMA-X to catch the patterns of the data. For nonlinear parts, we use neural network, ANN and ARNN, to capture the nonlinear trends of the residues obtained from the linear parts. The data we choose are the series of unemployment rates, COVID-19 cases, and inflation. Among them, COVID-19 cases and inflation act as new variables added into ARIMA-X models. Now let's see the preparatory work before modeling. First, time interval of training data series for UK and Singapore is from January 2020 to May 2021, but for the USA, it is from January 2015 to May 2021. The test interval remains the same for 3 countries. Secondly, for some new variables added in ARIMA-X, we do first-order difference just to ensure the series are stationary. In the table, we can see from the results highlighted in red that at least 2 tests support the stationarity. Thus, we consider these series stationary. After the preparatory work, we build the models. For each country, ARIMA, ARIMA-X containing COVID-19 cases, and ARIMA-X containing inflation are used to model the linear pattern. ANN and ARNN are used to model the residues. We also consider the original residues as part of the model. Then my teammate will show the model results and explanation.
Let's look at the summary of our results. First, let's look at the result of Singapore. In the chart on the left, the red line is the actual data of unemployment rate from June to October, and the lines in different colors show the predicted unemployment rate by different models, which are ARIMA, ARIMA-X with inflation, and ARIMA-X with COVID-19 cases. And different variety means different ways of dealing with residues. The green numbers are the final results with the least error. And there is a table showing values of error. So from the chart and the table, we can find that the green line is nearest to the red line, and the RMSE of ARIMA-X with COVID-19 cases is the smallest. So we pick it as the forecasting model for Singapore. For UK, similarly, we can find that ARIMA-X with COVID-19 cases fits best. The green numbers show final results of forecast. Our forecast of October's unemployment rate is 4.1. For United States, we can find that using ARIMA and fitting residues with ARNN is the most accurate one. The reason is that the dataset for USA is much bigger than the other 2. So we believe that using neural network to fit residues is more effective when we have more data. Finally, we can come to the following conclusions. First, during the pandemic, due to the huge impact of COVID-19, using ARIMA-X with COVID-19 cases can capture the change of unemployment rate better than ARIMA models. Second, for larger data sets, we can use neural network to capture long-time rules of data change. So we can improve our forecast in the following 2 ways. First is to enlarge our dataset, and second is to investigate the characteristics of macro environment and individual country. And then we can try to find more appropriate variables according to specific periods and country. That's all for our presentation. Welcome any questions. Thank you.